mathematics. How much gold can you hold in an elephant's ear? When it's noon on the moon, then what time is it here? If you could count for a year, would you get to infinity or somewhere in that vicinity? When you choose how much postage to use, when you know what's the chance it will snow, when you bet and you end up in debt. Oh, try as you may, you just can't get away from mathematics.
Hi, and welcome to another edition of Online Learning with Mr. Weeb. Hope you guys are having fun with the videos and you're able to watch them and you're able to get on to Connect. I know there's been some problems getting into Connect from time to time. Connect, the host site there, is working through their issues and trying to provide more ability and seamless ability to get on, and hopefully that will continue to improve over the next days and weeks. As we get into today's lesson, I first want to say yesterday, fairly straightforward lesson. Got no questions on the content yesterday, so that's very good. Appreciate that. And we'll continue going here now today. So yesterday we looked at Hooke's law, and of course Hooke's law simply stated that if we apply a force to a spring, it will stretch or compress, and the more force we apply, the more we can stretch or compress a spring. And so we had this graph, right? We had force, we had X being the amount of stretch or compression on a spring. And now if we think of it, because it's work being done, work is force times displacement, well, that means that the area under this line is the work being done to stretch or compress a spring. And of course the area, we all know how to find the area of a triangle in this case. It's a half height times base. And if we leave it at that, we can say, okay, we found a formula for the amount of work done to stretch or compress a spring. Well, work is a change in energy, right? We're changing the amount of energy. So the work done to stretch or compress a spring, what it's actually giving us to is equal to the amount of potential energy that is now stored in the spring, the amount of energy that now has the ability to do work on something else. And so instead of using area, we're going to write EE. EE stands for elastic energy, or energy elastic. And of course our formula is half F times X, but remember that F was K times X, and if we make that substitution, a half KX times X, we can simplify that down into 1/2 KX squared for elastic energy. That is our elastic potential energy formula, and it's a formula that you will want to add to your formula sheet. You'll want to write it down somewhere and have it handy as we're going to use it lots in the next little while. All right. So now that we have two kinds of energy, we have a kinetic energy and we have one of our two types of potential energy, we want to start now looking at the law of conservation of energy. So we're going to walk on over to the other whiteboard and we're going to start looking at the law of conservation of energy. So here we go. So over here on this board, we now have our law of conservation of energy. And again, it's pretty simple. Again, laws don't explain things, they just sort of state things, and it's up to us then to explain them with the science that we're going to do, with the equations we're going to formulate, and the problems we're going to solve. And so the law simply says that energy is not ever created or destroyed in any interaction. So anytime we have two or more objects interacting with one another, energy is not created or destroyed. It is merely transformed from one type of energy to another. So in our context, where we have a potential elastic energy, and we know a little bit about kinetic energy, we are now going to combine those two together. We're going to put springs and other objects together. We're going to stretch or compress a spring that's going to cause another object to move in some way, and we're going to combine and look at potential energy moving into kinetic energy, being transformed from one type to another type. So to do that, we're going to go back to the other board where I've got a sample problem ready to go, and we will see how that goes. Here we go. So over here we have our example problem. And so what we've got is we've got a block of mass 2.5 kilograms sliding across a smooth, aka frictionless, surface at 3 meters per second. When it hits a stationary spring bumper, whose spring constant is 360 newtons per meter, what amount does the block compress the spring? So here's our situation. We've got this block sliding across this surface at 3 meters per second. It's going to hit this spring bumper that's attached to the wall, and it's going to cause the spring bumper to compress in a certain amount, and we want to know how much it compresses. So the way we're going to do this is we're going to use the law of conservation of energy. The law of conservation of energy says that energy is not created or destroyed. This block that is moving at 3 meters per second has an amount of kinetic energy. As that block hits the spring, that kinetic energy is going to be transferred into elastic energy as it compresses the spring. Right? And when the spring stops, or when the block stops compressing the spring, all of the kinetic energy will have transferred into potential energy. And when we know that number, then we can figure out how far that spring is going to compress. So here's what we're going to write out. We're going to write out a formula. We're going to say, well, the kinetic energy of the block, okay, and you don't have to write block, you'll know that it is the block, but I'm going to write block for now, has to equal the elastic energy of the spring. All right, so when all said and done, all the kinetic energy of the block has to equal the stored potential energy that is in the spring. Now, if we use our formulas, we know that kinetic energy is a half mv squared. We know that elastic energy, just learned this, is a half kx squared. And if we look at our information that's given, we know the mass, we know the velocity of the block. We know what the spring constant is, given in the question. We don't know what the amount of compression is, but that's okay because that's what the question's asking us to solve for. So let's go ahead and fill in our numbers, and we'll get the answer here. We're gonna have a half times 2.5 kilograms times 3 meters per second squared, and that's gonna equal 1/2 times 360 newtons per meter times x squared. We'll go ahead and solve for x. I trust that you guys can do that. And when you do it, you're going to get a square root number. Right, you're going to take the square root of a number. And so what you'll get in the end when you write this out is you're going to get x equals to plus or minus 0.25. 0.25 meters. Okay. Because we're looking at a distance of compression, we get the plus or minus because we're taking the square root of the number. And again, it's a directional thing. We want the positive in this case again because we're looking at an amount, a distance that the spring is compressed, but it also works in terms of being positive in terms of that if we take moving to the right as our positive direction, the spring is compressing to the right, which would be a positive compression as well. So that's all we need to do. And this is the key right here, is being able to recognize what energy is being transferred into what other type of energy. As we move further into this, as we do some more stuff tomorrow before spring break, we're going to add our second type of potential energy, our third type of energy. And then we'll be moving between 3 types of energy. And again, it's important to remember that energy is always conserved. So at any point in a question, you can always set up what's the energy sort of before the interaction, and it has to equal the energy after the interaction. And if you remember that, then these will get quite simple. Your assignment for today is out of a handout of a different textbook. So again, you can find that on Connect. And I'll get that up there for you, and you can do it. And that's it for today. Tomorrow we'll have one more lesson, as I mentioned, and then on Friday we're going to try something a little different, and you can watch your email, and you can watch the Connect page for this. I want to have a little conference call with you guys. I want to use Zoom. I want to do a little check-in. It'll just be a short 15 to 20 minute, maybe half hour at the most check-in with you on Friday. We're going to do that at 10:30 in the morning. And so you can be prepared for that. If you don't already have a Zoom account, I would encourage you to get one. They're free. You just have to sign up with your email, and then we'll be able to do a little bit of a video chat session and check in on how things are going for you guys. And so we'll look forward to that. In the meantime, you're going to have an assignment on Connect to do, And we'll see you tomorrow when we'll add in gravitational potential energy. Have a great day. Oh, your verse of the day. Almost forgot. Can't forget the verse of the day. The verse of the day today comes from Psalm 94. That was pretty appropriate today. This is just I get these sent to me each day. Today's verse is Psalm 94, verses 18 and 19. It says, and again, this is David speaking to God. He says, when I said, my foot is slipping, your unfailing love, Lord, supported me. When anxiety was great within me, your consolation brought me joy. So I think that's a timely verse again today. In the midst of all the stuff that's going on, it's important to remember that God is with you, and He is supporting you. He has been with you a month ago. He was in control of things a month ago. He's in control of things today, and He'll be in control of things again tomorrow. And so let's keep that in mind, and have a great day. We'll see you tomorrow.